Imagine you're cleaning out an old cabinet when you uncover a phone buried beneath a layer of dust. You pick it up, turn it over in your hand, and wonder, when did I even buy this thing? You try switching it on, hoping to find a dated photo, an old message, or anything else that might give you a clue. If the battery is dead, you study the design instead. Does it have physical buttons? A touchscreen? Is it thick enough to double as a brick? Within seconds, you're already investigating the age of an object. But here's the problem. A stone tool has no screen to turn on, no photo gallery to search, and definitely no label saying, manufactured 3 million years ago. To an untrained eye, it may look like nothing more than a broken rock among thousands of others. So how do you make an object that has remained silent for millions of years reveal when it was made? That's when archaeologists become detectives of deep time. They don't simply pick up a stone, stare at it for a few seconds, and guess an impressively large number. They examine the soil beneath it, the objects surrounding it, its chemical composition, and sometimes even traces of energy produced by particles arriving from space. That may sound like an extraordinary amount of effort for one rock. But this is only the beginning. To unlock the past, scientists rely on two main sets of tools. The first is relative dating, which tells us whether one object is older or younger than another. The second is absolute dating, which attempts to assign an actual age something like 3 million years. One method puts events in order. The other tries to place numbers on the timeline. Now, let's open both toolkits and see how they work. We'll begin with Earth's giant layer cake, better known as stratigraphy. Picture the ground as an enormous cake assembled slowly over thousands of generations. Sand blows in. Dust settles. Leaves decay. Rain spreads fresh layers of mud across the surface. Little by little, new material piles on top of the old, quietly preserving the sequence of everything that came before. The basic principle sounds almost suspiciously simple. Layers near the bottom are usually older than the layers above them. If a stone axe is discovered in the 10th layer down, it is probably older than an object found in the 5th. Things that arrived earlier generally had more time to become deeply buried. Archaeologists are therefore reading a very unusual book starting with the newest pages at the surface and digging backward into the older chapters below. You can also think of it as a laundry basket. The shirt you wore today is sitting near the top, while the one you threw in on Monday has disappeared somewhere near the bottom. To reach it, you have to dig through an entire and possibly embarrassing history of your wardrobe. Archaeologists do something similar. Their laundry basket just happens to be the size of a valley. But wait, Earth does not always keep its layers neatly organized. Floods can wash sediment away. Burrowing animals can drag old objects toward the surface. Tree roots can twist through the ground and disturb everything around them. When the layers have been scrambled, scientists turn to another technique, comparing styles. They study the shape of a tool, examine how it was made, and match those features with other tools whose ages are already known. It's a little like looking at an antique bicycle and immediately knowing it probably wasn't built last week. Stone tools had their own technological fashions. Earlier tools were often large, heavy, and roughly shaped, while later ones could be smaller, more balanced, and sharper. Manufacturing methods changed from one period to another because, even in prehistory, technology refused to stand still. Still, these methods only tell us which object is older. That's like knowing you're taller than your younger brother without knowing your exact height. To say that a tool is 2 million or 3 million years old, scientists need clocks hidden inside matter itself. And that is where the story enters the world of atoms, radioactivity, and numbers so enormous they almost stop feeling real. Now let's travel to Kenya, where one of archaeology's strangest discoveries began with something completely ordinary: a wrong turn. In 2011, a research team accidentally headed in the wrong direction across the dry landscape near Lake Turkana. Instead of immediately turning back, they kept looking around and noticed stones marked by unusual patterns of deliberate striking. At a site known as Lomekwi 3, those tools were eventually dated to roughly 3.3 million years ago. Getting lost is usually an inconvenience. This time, it changed the story of human history. But here's the truly strange part. These tools appeared far earlier than scientists had previously believed our ancestors began shaping stone. They even predated the genus Homo, the group that includes modern humans. Think about that for a second. Some creature was selecting stones, lifting them, and striking them with intention 3.3 million years ago. So who made them? Was it a very early human ancestor or another branch of the family tree that we still barely understand? To answer that question, scientists couldn't simply stare at the stones and say, well, those look pretty old. They needed a much more reliable clock. Fortunately, this part of Kenya once had an extremely noisy neighbor, volcanoes. Whenever one erupted, ash fell across the landscape like a vast blanket. Once that ash cooled, hardened, and became rock, it formed an almost perfect marker in time. The secret lies in the eruption's intense heat. While volcanic material is still hot, gases trapped inside its minerals can escape, bringing the chemical clock close to zero. The moment the ash cools and hardens, that clock begins ticking again. It is like pressing the reset button on a stopwatch, except this stopwatch can run for millions of years without ever needing a new battery. One of the best-known dating techniques uses potassium and argon. Radioactive potassium inside the rock slowly transforms into argon gas at a predictable rate. Scientists measure how much potassium remains and how much argon has accumulated, then work backward to determine when the rock cooled. If a dated layer of ash lies above a stone tool, then the tool must be older than that layer. But wait, that still isn't the only evidence. This method works especially well for extremely ancient rocks, when the timeline stretches across millions of years. But what if the object is only around 40,000 years old? A bone fragment, a tooth, or a piece of charcoal from an ancient fire does not require a volcanic clock. It needs something more sensitive, something designed for a much shorter span of time. And that is when carbon-14 steps onto the stage. Think of it as the food clock. While alive, plants absorb carbon from the atmosphere. Animals eat the plants, humans eat both, and carbon moves through the food chain like a guest who never seems ready to leave. A tiny portion of that carbon is the radioactive isotope carbon-14. As long as an organism remains alive, its supply is constantly replenished. But the moment it dies, that supply stops. From then on, the carbon-14 begins to decay like a battery slowly losing its charge. Roughly every 5,730 years, half of the original amount disappears. Scientists measure what remains and use it to calculate how long ago the organism died. In this way, a bone or piece of charcoal found near a tool can help date prehistoric activity at the site. The problem is that stone was never alive, so a stone tool itself cannot be dated directly with carbon-14. So what happens when a tool is found alone, inside a cave with no bone, no charcoal, and no conveniently placed layer of volcanic ash? Here's where it gets interesting. Instead of trying to date the stone itself, scientists turn to the grains of sand surrounding it. Because sometimes the smallest, most ordinary-looking material is carrying the exact clock they need. Grains of sand can store energy produced by natural radiation in the surrounding soil. As long as they remain buried in darkness, that energy gradually builds up inside their mineral structure. In the laboratory, scientists shine a special light on the grains, causing the stored energy to escape as an extremely faint glow. In general, the more energy released, the longer the sand has been buried. The technique is called optically stimulated luminescence, and it is essentially a way of asking a grain of sand, when was the last time you saw the sun? Imagine each grain of sand as a tiny locked box. The last time it sat in sunlight, that light emptied all the stored energy inside, resetting its internal clock to zero. Then the grain was buried, cut off from the sun, and began quietly measuring time in the dark. In the laboratory, it releases that stored energy as a faint glow. By measuring the glow, scientists can estimate how long the sand has remained buried and, in turn, when the stone tool beside it was left behind. But that's only part of the story. Some ancient tools were made from obsidian, a glossy black volcanic glass so sharp and dramatic that it looks like something from a fantasy film. Ancient toolmakers prized it because a broken piece could produce an exceptionally fine cutting edge. Obsidian also has one very unusual habit. It slowly absorbs water from its surroundings. You might call this the thirsty glass method. The moment an ancient craftsperson struck a block of obsidian, a brand new surface was exposed. From that instant, water molecules began creeping into the glass, forming an incredibly thin layer of hydration. Think of the strike as peeling the protective film from a new phone. Once the surface is revealed, the clock starts running. The toolmaker had no idea, of course, that the blow had just activated a timer that could continue for thousands of years. Scientists remove an extremely thin slice from the tool and examine it under a microscope. The thicker the hydration layer, the longer the surface has had to absorb water. It sounds straightforward, but there's a catch. The absorption rate also depends on temperature, humidity, and the chemical composition of the obsidian itself. A tool in a hot environment may drink faster than one in a cold region. Researchers therefore have to calibrate the method for local conditions before assigning an age. But wait, beyond soil, sand, volcanoes, and glass, scientists also use a clock so large that we are standing on it right now, Earth itself. Our planet behaves like a giant magnet with a magnetic north and south pole. Yet throughout its history, those poles have reversed many times. Compasses would have pointed in the opposite direction, and migrating birds probably would not have appreciated the confusion. For scientists, however, those reversals created remarkably useful markers in time. Soil and rock contain iron-rich particles far too small to see with the naked eye. As sediment settles or volcanic rock cools, these particles align with Earth's magnetic field, like millions of microscopic compass needles. Once the material hardens, their direction becomes locked in place. Even if the planet's magnetic field later reverses, the particles preserve their original alignment, a snapshot of which way the ancient compass was pointing. Scientists measure the magnetic direction preserved in each layer and compare it with the global record of known magnetic reversals. At Lomekwi, the magnetic evidence helped place the tool-bearing sediments within a period dating to roughly 3.3 million years ago. When stratigraphy, volcanic layers, and magnetic data all point toward the same window of time, the conclusion becomes far more convincing. One witness may be mistaken. 3 independent witnesses telling the same story deserve attention. But why go to so much trouble just to learn the age of a rock? Why dig beneath the scorching sun, measure argon gas, firelight at grains of sand, and study compass needles smaller than dust? Because the number is never just a number. Each date is like a pin placed on the map of evolution, showing us when a new ability first appeared among our ancestors. Every deliberately shaped stone is evidence that some creature in the distant past saw the world differently. It did not simply see a rock. It saw a tool that did not exist yet. It may have understood that striking one spot could produce a sharp edge useful for cutting meat. That requires imagining a result before taking action. In other words, a stone tool preserves more than the skill of a pair of hands. It carries a faint record of a mind at work. To make a useful tool, the craftsperson had to choose the right stone, hold it at the proper angle, and strike it with just enough force. Too softly and nothing happened. Too hard, and the entire stone might shatter, not an ideal outcome after traveling a long distance to find good material. Ancient toolmakers had to recognize fractures, predict where a flake would break away, and coordinate their eyes and hands with precision. A sharp stone edge was not a lucky accident. It was the product of observation, practice, and logical thought. And even that was not the limit of their ingenuity. Ancient toolmakers did not simply create sharp stone blades and hold them in their bare hands. They learned to attach stone points to wooden handles using tree resin, beeswax, or heat-treated birch tar. In other words, they invented prehistoric superglue tens of thousands of years ago. Doing that required finding the right ingredients, controlling the heat, and combining the materials properly. It sounds simple until you try making glue in the wilderness without a lighter, a metal pot, or an instructional video. But how do we know what these tools were actually used for? The answer lies in scratches far too small to see with the naked eye. Under a microscope, a stone edge may reveal signs of slicing meat, striking bone, shaving wood, or cracking hard seeds. Sometimes scientists even detect traces of proteins, fats, or plant tissue trapped on the surface. A stone that once seemed completely silent can suddenly reveal the menu of the person who held it. This is where science stops looking like a page full of numbers and starts feeling like a conversation with the past. Geology tells us where a tool belongs on the timeline. Chemistry measures the changes taking place inside matter. Physics reads light, magnetism, and radioactive decay. When those fields come together, an ordinary stone is no longer just a stone. It becomes a witness that has been waiting millions of years to be questioned. Of course, a single witness can be misleading. A flood may disturb a layer of soil. A sample may become contaminated. A dating method may be affected by heat or local conditions. That is why scientists rarely trust just one clock. They combine stratigraphy, volcanic ash, magnetism, luminescence, and evidence from surrounding materials. It is like interviewing several people who all saw the same event. When every witness tells the same story, the conclusion becomes much harder to dismiss. And here's where it gets especially interesting. Every time a new dating technique appears, the history of humanity may need to be rewritten. For years, the oldest known stone tools were thought to be about 2.6 million years old. Then Lomekwi entered the story with a date of roughly 3.3 million years. Suddenly, the opening chapter of technology moved back by about 700,000 years. Science has a slightly inconvenient but essential habit. When the evidence changes, it is willing to admit that the old story was wrong. That means technology began far earlier than we once imagined. Creatures that still possessed many ape-like features may already have been choosing stones, planning their strikes, and shaping objects for specific purposes. The Lomekwi tools may look crude beside a smartphone, but at the level of the idea, they are strangely similar. Both begin with the same act: taking material from nature, reshaping it, and using it to extend the abilities of the body. And perhaps our hands helped make our brains more intelligent. Shaping stone requires the eyes, hands, memory, and powers of prediction to work together. A failed strike forces the toolmaker to adjust. A successful one can be remembered and repeated. Across countless generations, toolmaking may have helped strengthen the mental abilities involved in movement, planning, and learning. The hands did not merely follow instructions from the brain. They may also have helped train it. Think about that for a second. Without those first shattered stones, there might have been no axes, sewing needles, wheels, machines, or eventually smartphones. The journey from a sharp stone edge to a silicon chip did not happen in a single leap. It unfolded through millions of years of tiny improvements. Each generation inherited an old idea, changed it slightly, and passed it forward. So nearly everything you use today carries a faint trace of that first deliberate strike. A pen allows the hand to preserve thought. A vehicle allows the legs to travel farther. A computer allows the brain to process more information. Tools have always done the same basic thing. They push the body beyond its natural limits. We do not have claws, powerful fangs, or thick armor. Instead, we build what nature forgot to give us. Humans are a strange species, but we are remarkably good at compensating. In the end, the question, how old is this stone tool, leads to a much larger one. What makes us human? Perhaps the answer is not found only in the shape of our bodies or the size of our brains. Perhaps it lies in our ability to look at an ordinary object and imagine what it could become. The next time you pick up a phone, a pair of scissors, or even a spoon, remember that each belongs to a story that began with a broken stone millions of years ago. We did not simply learn to use tools. We evolved alongside them.